You toss a handful of white crystals on frozen pavement, and the ice just disappears. It is not magic. It is physics. Every winter, cities dump millions of tons of salt onto frozen roads. It works so well we take it for granted. But here's the strange part. Salt does not heat the ice. In fact, mixing salt and ice makes the mixture colder than plain ice, sometimes dropping all the way down to minus 21 degrees Celsius. And yet, the ice melts. How can something get colder and melt at the same time? The answer has nothing to do with temperature and everything to do with how water molecules behave when you invite a stranger to the party. Pure water freezes at exactly 0 degrees Celsius. At that point, water molecules slow down enough to lock into a rigid crystal lattice. That is ice. But freezing is not a one-way street. Even in solid ice, molecules are constantly trying to break free, and in liquid water, molecules are constantly trying to lock back into place. At 0 degrees, these two rates are perfectly balanced. Now drop salt into the picture. Salt dissolves into sodium and chloride ions, and those ions physically get in the way. They block water molecules from lining up into that neat crystal lattice. Freezing becomes harder. Melting becomes easier. The balance point, the temperature where ice and water can coexist, drops below 0. Scientists call this freezing point depression. Here is what actually happens on a salted road. Ice is never perfectly dry. There is always a thin microscopic layer of liquid water sitting on top of any ice surface, even at minus 10 degrees Celsius. When salt crystals hit that layer, they dissolve into a concentrated salty liquid called brine. Brine has a much lower freezing point than pure water. So now you have a liquid that refuses to freeze sitting on top of a solid that is perfectly happy to melt. The brine pulls heat from the ice to keep itself liquid, which forces more ice to melt, which creates more brine, which melts more ice. It is a chain reaction that happens as long as the air stays warm enough and enough salt is present. But salt has a hard limit. The more salt you add, the lower the freezing point drops, until you hit a specific ratio called the eutectic point. For ordinary table salt and water, that magic ratio is about 23% salt by weight, and the freezing point bottoms out at minus 21 degrees Celsius. Go any colder than that, and no amount of salt will save you. The brine itself freezes solid. This is why road crews in Minnesota and Canada stop using plain salt once the pavement drops below roughly minus 10 degrees, because the chemistry simply stops working. In those conditions, they switch to calcium chloride or magnesium chloride, which can push the freezing point all the way down to minus 50 degrees. The genius of road salt is that it does not have to melt ice quickly. It just has to prevent the thin top layer from refreezing. Cars drive over the brine, breaking up the weakened ice, and the sun and friction finish the job. It is cheap, it is abundant, and it scales to entire highway systems. But there is a cost. Road salt runs off into rivers, damages concrete, corrodes cars, and poisons roadside soil. The United States alone spreads more than 20 million tons every winter, which is roughly 130 pounds of salt per person per year. That same molecular trick that keeps you from slipping on your driveway is quietly rewriting the chemistry of every freshwater stream in the Northern Hemisphere. If you enjoyed this trip into everyday physics, subscribe to Curious Science. Next up, we dig into why hot water can actually freeze faster than cold water.